like, so here, for example, this slide shows two examples of the same chemically the same material, yeah, silicon dioxide, or sometimes can also be called quartz, yeah, depending on the structure. If it is all periodic and crystalline, we can call it quartz. But if it is amorphous, usually we call it glass, pure glass. Although the glass that we use in our houses and our daily life, usually they are not pure silicon dioxide. They have other impurities. They have other impurities from sodium, potassium, etc. So the glass that we use, yeah, in our daily life, for example, to drink, and as also as a material for building material, yeah, that is light transparent. Usually they are not crystalline. They are in amorphous state. What we call as amorphous state, because they don't have periodic packing, and hence also they can pass through light easily. Yeah, some of them. This also we have learned last week, yeah, about the 7 crystal system, the 14 crystal lattices, the lattice constants, A, B, C, and we have classified the 7 crystal system and and the 14 crystal lattices. Okay, this is the 7 crystal system and their characteristic, and then the crystal lattices, the crystal lattices 14 is here. So not every crystal system has the same number of crystal lattice. Yeah. Some has 3 or 4 crystal lattice. Cubic has 3 crystal lattices. The simple cubic, body centered cubic, and face centered cubic. Orthorhombic has 4 crystal lattices. Simple orthorhombic, body centered orthorhombic, base centered orthorhombic, and face centered orthorhombic. Then we have tetragonal, rhombohedral, hexagonal, monoclinic, and triclinic. So we have discussed this. We have shown this, the 14 standard unit cells. Okay, so hopefully you have reviewed the slide. And then we have learned last week on how to indicate positions within that unit cell, which is basically indicated by using the unit distances. So if it is exactly at the corner, then it will be 1. The corner of the cubic, for example, in this case, then it will be indicated by number 1. Or if it is in the middle, then it will be half. If it's 1/3 of the unit lattice, it will be 1/3, etc. And for each of the 3 axes, they are shown as separate numbers, yeah, and separated by comma, and all are then located within parentheses. Okay, then we have also learned how to express direction within a unit cubic cell, okay? And how the factor that connects to lattice point can be expressed also in number and then located within bracket. Positive and negative directions are not the same, and they have to be integers. Yeah, and that is why we have to round the numbers within that bracket so that they are represented as integers. Okay, then finally last week we have learned how to express plane, yeah, how to express Miller indexes. Okay, and we have learned how to identify the crystal planes. Yeah, somehow from the assignment or homework of the group 2, yeah, I think Andy with Angeli still got it wrong. I have put comments. Have you learned the comments from me, Angeli, and Andy?
Yes, sir.
Okay, do you know the mistake that you made?
Yeah, already.
Okay, so yeah, So you have to be able to do both directions. That means if given this picture, identify the the Miller indexes, you have to be able to write it down. On the other hand, if the Miller indexes is given, you have to be able also to draw the plane within a single cubic unit cell or single unit cell. Okay, and of course to check it, that you just go to with the other direction, with the reverse direction. If it match, then it is correct. And that is the easiest way to check whether your answer is correct or wrong. Yeah, so we write the Miller indexes by determining the intercept in the XYZ, and then form the reciprocal, and then clear the fraction, and then determine the small set of the whole numbers. So example have been given last week also about how to make Miller in how to determine and calculate Miller index in cubic unit cell. Okay, so let's go into the detail of this crystalline structure. How can we stack metal atoms to minimize the empty space? So basically, in the most equilibrium condition in any solid state material is that they have to be always in the most stable condition in terms of energy. So they found the most comfortable. Yeah, we call it in layman's term. It is most comfortable. Yeah, most comfortable, and in this case, in terms of thermodynamic, we express it as the minimum energy. And then in the case of solid state, it is often that the metal atoms, for example, in a metallic material, they try to minimize the empty space between them. Okay, so for example, when we stack atoms in 2 dimensions, let's say if you have what do you call it, Kelereng in English, like balls, small balls, ping pong balls or the small balls. When you arrange them in 2 dimensions, you have 2 possibilities. One is to arrange like this, more or less is it looks like a hexagonal, right? Hexagonal arrangement here because an individual ball is surrounded by 6 other balls. Alternatively, you can arrange it like this, square like 3D structure, yeah, where each of the ball is surrounded by how many? 8 other balls. Here we see that the first one in 2 dimensions has the minimum empty space compared to the second one, this square one. But since we speak about 3-dimensional structure in metallic material, so we have to stack them, and we have to make stack them. So each of these will become one single layer of the 3-dimensional structure. So for example, in metallic crystal structure, they tend to be densely packaged. Yeah, and why they need to have dense packaging? Because usually only one element is present within a metallic material. Yeah, so that is why then all the atomic radii here, radius, yeah, the plural of radium, radius, then they are the same. And we see that we have learned from the previous chapter that metallic bonding is not directional. So the nearest neighbor distances tend to be small in order to lower this bond energy. Yeah? The nearest neighbor distances that tend to be small. Remember this graph. Yeah. So in order that the bond energy is small, they have to reach this optimum distance. Yeah, this optimum distance where the energy is minimum. Energy minimum means it is the most stable configuration. Of course, it cannot get closer because if it gets closer than that, there start to be repulsive forces between the atoms. Okay. So Electron clouds, the other reason, the fourth reason of why the dense packing could happen in metallic crystal structure, because electron cloud shields the cores from each other. Yeah, they are the core here, the nucleus, the proton, the positively charged nucleus, which contain mostly proton and neutrons. They are being shielded by these electron clouds that are shared by the atoms. Yeah. And that's why the metallic crystal structure usually have the simplest crystal structure. There are three different structure in metal that we will examine in this slide. First is the simple cubic structure. So in simple cubic structure, basically the layer looks like the square one. Yeah? The two-dimensional layer looks like the square one, in which case then each of the atom is surrounded, in two-dimensional is surrounded by 8. But in 3 dimensions, since you stack them, stack one by one, yeah, then for example, if I'm not sure if I can try to draw it. So, for example, yeah, then let's draw the next layer with different color. The top, the upper part, yeah. For example, this is, imagine it in 3 dimensions. Yeah. The second layer will be located exactly above the first layer of atom. Okay, and similar than the bottom layer, the lower layer than that will be also example is imagine it in 3 dimensions. Yeah. I'm not a good drawer, so please bear me with this. So etc. So in this case, then that they are exactly located above one another. So the position of the atom is one layer of the atom is exactly at above the atom at the another layer. So it means if we look in 3-dimensionally like this, it becomes like this. So each atom, yeah, will be what do you call it, surrounded by how many? Within the same layer, it is surrounded by 4 nearest atom. Yeah? 1, 2, 3, 4. And then from the above layer, there is 1 atom above it. From the bottom layer, there is 1 atom below it. So in total, there are 6 nearest neighbors atom. Yeah, this is called the simple cubic structure. However, this is quite rare in metal because the packing density is small. It's not completely packed, as you can see here. The empty spaces, even between one single layer, the empty spaces between the atoms are relatively larger compared to if we pack it hexagonally like this. Let alone if we pack in 3 dimensions, then there are more larger space in between the atoms. Okay, so the close pack direction are cube edges. Okay. So usually here it is mentioned that only polonium has this kind of simple cubic structure. Yeah, so we call it the nearest neighbors here as coordination number. So remember, coordination number. So in simple cubic structure, the coordination number is 6. So then if we want to assess how dense, how closely is atom being packed in such crystalline structure, we can use this parameter to assess. It is called as the atomic packing factor. So in atomic packing factor, yeah, is defined as the volumes of atom in unit cells divided by the volume of unit cells. The higher the volume of atom in unit cells, so it is a fraction. Yeah? Compared to the higher the fraction, it means the more space in that unit cell is occupied by atom. And it means the atomic packing factor is larger. Okay. And this, of course, it is assumed that the atom is hard space. In reality, of course, it is not, because the electron is always encircling, yeah, revolving around the nucleus. So there, one time there was always empty space actually. But here in this model, we assume it is a hard sphere. So the APF for simple cubic structure is 0.52. And how is it derived? So here, if we have in a single unit cell, yeah, so a single unit cell means in this case, for example, wait, yeah, a single unit cell here is, yeah, like this. So for example, here between this, and this is a single unit cell. How many atoms are there? Can you guess? Within the single unit cell. So another neighboring unit cell will be, example, this one. This one is the neighbor. Okay. Maybe not that clear. Okay, this different color. Another neighboring unit cell is this one. Okay, Ezra, how many atoms are there within this single unit cell?
Single unit cell 8, sir.
It's atom.
Mm-hmm.
Grace, do you have any other opinion? Is it correct? Do you think what Ezra said, that one single unit cell like this has 8 atoms here in this simple cubic structure? What do you think, Grace?
Satu, sir.
Huh?
Saya bingung, sir.
Masih belum menang. Jadi kayak masih
Saya
nggak.
bertetapan pada 8, sir. I don't know.
8 or how many? 8. You mentioned 8, right?
Yeah. But you
Grace, what do you
mean
think? How many of them?
No idea yet.
Why no idea? It is clear here, right? From this picture.
What is it the circle in the edge? 8.
8.
Oh.
Yeah. Andy, what do you think? How many atoms are there in one single unit cell?
8, Pak.
8. Okay. Anjali, how many? Anjali, are you there? Mana Anjali ini? Hilang lagi. Anjali? Hello? Hello? I think it's in toilet. So is it correct that, so okay, 3 of you have answered that one single unit cell is 8. Yeah, it is correct, but not yet, not really correct. Yeah, how many a single unit cell, how many atoms does a single unit cell have according to this picture? Can you not open your microphone, Anjali? Hello, Anjali? Anjali, are you there? Can you answer the question? You can answer via the chat if you want. How many atoms does a single unit cell here in the simple cubic structure have? Yeah, okay. How many? Can you write it down there in the chat if your mic is broken? According to your guess. Quick, just throw an answer. It's not quiz. It's not. How many do you think? Do you agree that it is 8, like the others have answered? Hello, Anjali? Anjali, can you answer? Opinion. Okay, so yeah, in one glance, it might be correct, yeah, because it seems to be there are from this drawing, there are 8 atoms, yeah, within a single unit cell. But you have to see deeper and closer. Okay, I have drawn here, for example, that within this picture, actually there are how many unit cells? 8 unit cells, right? 1, 2, 3, 4, 5, 6, 7, and then 8 at the farthest most. So it means what? It means actually one atom within this one position is not owned by a single unit cell. Okay, one atom in this position is shared by how many unit cell? So one atom, let's say this red one in the middle, the red atom in the middle. It is shared by how many unit cell? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the share of the atom that is owned by a single unit cell is 1 divided by 8, which is 1 divided by 8 is 1 over 8. And since, yeah, there are 8 atoms located at the corners of the unit cell, then this is multiplied to 8. So actually the total number of atoms within a single unit cell is 1. Okay. Yeah. So here, yeah, as we can see here, this is the picture of a single unit cell. Okay. So if we draw a single unit cell only, the corner at the corner, what is there only is only 1/8 of the total atom, right? The other 7 over 8 is owned by the other 7 unit cell in the neighboring vicinity of this unit cell. Okay, so it contains 8, but each of these 8 corners, yeah, each of the corner only contain 1 over 8 of atoms. That's why the total number of atom per unit cell is only 1. Yeah, okay. Excuse me. So, based on the definition of atomic packing factor, we continue with the calculation of the nominator. The nominator is the volume of atom in unit cell, which will then equals to the number of atom per unit cell, which is in this case is 1, and then the volume of a single atom. If we assume it is a hard sphere, it's a ball, a hard ball sphere, so which is then 4 over 3, yeah, from the volume of ball formula, 4 over 3 times pi, and then the radius of that atom, cubic. Now, how to find the radius? So this is basically the radius cubic. How to find this radius? So in a single cubic, in a simple cubic structure, okay, in 2-dimensional, the atoms is attaching to each other, okay, attaching to each other. So like this, in one edge, like this here, also here, they are attaching to each other. It means one unit lattice here, a single lattice unit A equals to 2r, because this is r, right? This is the radius of the atom. This is also r. This is r. Yeah, okay. So means A equals to 2r. The radius equals to the radius equals to A over 2, half of A. So usually in crystalline, in material science, the data that is given is the unit lattice. The data that is given unit lattice. So we put r cubic here equals to A over 2 cubic. The volume of the unit cell itself is in simple cubic structures, and this is A cubic, yeah, A times A times A cubic. So this can be simplified basically like this, and 0.5 cubic is how many? Anyone has calculator? Let me calculate also.
Is it 1.25?
1.25, yeah. 0.5 square times 0.5. 0.125, yeah, 0.125. So this is 0.125 times pi times 4 divided by 3. Okay, so times pi times pi. Wait, sorry, 0.125 times pi times 4 divided by 3. Yeah. Why it is 0? 0.125 times pi equals to 0.392 times 4 equal to 1.57 divided by 3. Yeah, 0. We obtain 0.5236. 0.5236 more or less. This is actually long. So yeah, and this is the approximate atomic packing factor for a simple cubic structure. Okay. So you see here that just above half of the volume within that unit cell is occupied by the atom. The other 0.48 mostly is just empty space. Yeah, not even gas, yeah, because this is completely packed. Yeah, there's no other thing can enter it. Yeah, except later as an impurity. Okay, then consider then the next structure, yeah, for metallic crystal is body center cube. In the body center cube, besides if we consider a single unit cell like this, a single unit cubic cell, the atoms is occupying not only the corner of the cube, but also the center of the cube. That's why it is called the body-centered cubic structure. There is an atom also here at the center. So here, how many atoms per unit cell? We remember that each of the atom here in the corner is shared by the other 8 neighboring unit cells, right? Not only to the side here, but also on to the above it. So this is shared by 8. So this is shared by 8 means the share of that unit cell of from that atom is only 1/8. And there are 8 of it. There are 8 of them that having this kind of position. So this is 1/8 times 8 equals to 1. And we have 1 atom in the corner that is completely owned by that unit cell. So this is completely 1. Yeah. The total we have 2 atoms per unit cell. So it seems now that per unit cell, it contains more atoms. Yeah. So in this case, the packing happens along the cube diagonal. So along this cube diagonal. Yeah, or like that. Here, if it is drawn like this, from this atom, along that cube diagonal, the atoms touch each other. So here all atoms are identical. The center atom is shaded differently only for ease of viewing. Typical examples are chromium, tungsten, iron in its alpha phase, tantalum, and molybdenum. The coordination number is 8. Why? Because each of these atoms is neighbored, or there are 8 atoms on its vicinity, on its neighboring vicinity. 1, 2, 3, 4, 5, 6, 7, 8. Here also it has 8. 1, 2, 3. Where is it? So this also 8. Yeah. If we draw completely three-dimensional, each of the atom is surrounded by 8 other atoms. So the number of atoms per unit cell is again how many? 2 atoms per unit cell. Now, if we calculate the atomic packing factor, the APF is 0.68. So it has larger APF compared to simple cubic structure. Where does it come from? The number of atoms per unit cell is 2. The volumes of atoms is 4/3 pi, yeah, from the volume formula of a ball, and R cubic. And to find R cubic, we get it from the cubic diagonal, along the cube diagonal. Because along the cube diagonal, the atoms touch each other. And from cubic formula, we know that we can derive. This is the side diagonal, right? This is the lattice side. And this is the, what do you call it? Side diagonal. So if we have like this, since how to calculate this, we have to calculate this first, right? And this calculate this. This is A. This is A square 2, right? Because it is calculated from A and A here. So this cube diagonal will be A square root of 3. And A square root of 3 here equals to how many R? So this is R. This is 2R basically, right? Because this is one single diameter of the atom and this is R. In total, this is equal to 4R. So the R equals to A over 4 square root of 3. So this is put inside the bracket, and then make cubic divided by the volume of the unit cell, A cubic. So we obtain 0.68. So if you compare with the simple cubic structure, which is only APF of 0.52, the APF of the body center cubic is larger. So it means more space inside BCC is occupied by the atom. Then we consider face center cubic. This is the one of the three structure, the third structure, which has shared by more metals. So in this case, besides the atoms that are located in the corner of the cubic, we have also atoms that are located on the center of the edge. Center of the face of the side of the cube. So this way, this is the atoms that is located in the corner, and we have here the atoms that are located on the face of the side of the cube. So atoms touch at the side diagonal, not or face diagonal, not cube diagonal. And so it means it's like this. This is like this. So if this is R, this is also R, this is R, this is R. So A square root 2 equals to 4R. So later, when we calculate the atomic packing factor, the R here equals to A square root 2 divided square root of 2 divided by 4. Okay. Examples are aluminum, copper, gold, lead, nickel, platinum, and silver. The coordination number is 12. Where does it come from? I will let you to figure out yourself. For example, it means each of these atoms is surrounded by 12 other atoms. This is on only 4 of it. 4 of them. 1, 2, 3, 4. Where are the other 8? This is from the surrounding, the neighboring unit cells. Okay. The number of atoms per unit cell, we have atoms at the corner, which is set by 8 unit cells. So it means 8 times 1 over 8 is equal to 1. We have at the side of the cube, how many? 1, 2, 3, 4, 5, 6. 6. And each of these atoms is shared by how many unit cells? 2 unit cells. With the adjacent unit cell. So each of these atoms share per unit cell is only half. So this equals to 3. So the total number of atoms per unit cell, per single unit cell, is 4. This is 6 atoms at the face times the half of the share per unit cell plus 8 at the corner times 1 over 8 per unit cell. Okay, then the atomic packing factor is 0.74. Where does it come from? So this we have calculated like earlier here. So R equals to A square root 2 divided by 4. So then if we put into the formula of ATF, atomic vacuum factor, so the volume of the atoms per unit cell equals the number of atoms at that unit cell, which is 4, times the volume of each of the atoms, which is 4 over 3 pi square root of 2 times A over 4 and cubic divided by A cubic. And we obtain this number, 0.7. So from here, we see that FCC has the most densely packed crystal configuration compared to the other two, the simple cubic structure and the body center cube. So far, understand? Any questions?
Sir, can you explain a little bit again about
Sorry, can you speak louder, please?
About the coordination? Tadi nggak nangkep yang coordination.
Coordination is the number of atoms on the vicinity of an atom in that crystals. So let's see the simple here in the simple cubic structure. Each of this atom here, each of this atom is surrounded by how many atoms? 1, 2, 3, 4, 5, 6. 4 on its same plane, and 1 on its above, and another one beneath it. Okay, this is simple cubic. The coordination number is 6. Body center cube, you have to draw multiple lattice, multiple cells in order that you can calculate the coordination number. So in body center cube, on the other hand, for example, it's easy. You just pick, for example, the atoms at the center and see that it is surrounded by how many atoms? 1, 2, 3, 8. 1, 2, 3, 4, 5, 6, 8. 4 on its above layer, 1, another 4 on its on layer beneath it. Okay. What about face center cubic? It's 12. Now this is not that easy to find out. You have to draw again here at the unit cell, for example, above it. For example, if you know what is the atom neighboring this, okay, so it has this one. This is not that easy, okay, to perceive by our mind. So you have to draw it in 3 dimensions so that you know how many atoms are there. So for example, here 1, so 1, 2, 3, 4. For example, in the vicinity of this atom, 1, 2, 3, 4 in this plane. Then we have another 4 in this plane. 1, 2, another 3, 4. Then we have another 4 at this edge. 1, 2, 3, 4. So total 4 times 3 is 12. Can you imagine in your mind? I cannot draw it. I'm not that drawer. If I draw, then you will get more confused.
Okay. Lumayan.
Huh?
Ya, oke. Harusnya bisa.
Yeah, if you are a good painter or good drawer, try to draw on your own, or otherwise you can write a program to draw each of this point of this atom in coordinate and find the closest, how many atoms are in its vicinity. So that is coordination number. Okay, so we have learned now the atoms per single unit cells. Okay, the time is up for this session. So let's have